We have Victor Medina. Who's going to be giving us a lunch and learn presentation. He is a person that I worked with in a prior life. He's was one of the senior scientists for the Corps of Engineers, the ERDIC, Engineering Research and Development Center in Vicksburg, Mississippi. He's also one heck of a tennis player.
Thank you.
Spent a lot of lunch times playing tennis with them. And so he's done a lot of amazing work over the years. He's recently gone private. And so he's going to tell us a little bit about the history of PFAS and other remediation technologies and techniques that he's developed. So with that, I will turn it over to Victor.
Thank you. Thank you, everybody. I'm going to share my screen. Okay, do you see the presentation, you guys?
Yes, we do.
Okay, I'm going to put on slideshow. Is it showing up on your, looking good on your screens?
We're seeing the presenter view, I think.
Well, okay. How do I change that?
Switch screens, display settings.
Display settings. Woo. Yeah, there you go.
There
Okay,
you go.
swap
Swap presenter. There you go. Yep,
Oh
that's it.
yeah, got it. Okay.
Beautiful.
Thank you, guys. So I'm very happy to be here. My name is Victor Medina, and yeah, if I could. Oh, okay. Yes, I'm the CEO and managing member of my companies. I live in Brandon, Mississippi, and I also work in Brandon. Thank you very much for joining. This is me. I'm the owner and environmental engineer at Medina Environmental Consulting and Solutions. And then I have a second company, MDT Technologies. I'm the majority owner, CEO, and managing member of that organization. In both organizations, we value high quality environmental services. And then my MEX organization, we do research to develop environmental technologies, and the MDT company focuses on developing those into products and services so that, like, for example, we would build a water treatment system, but also if it's needed, do turnkey operation, that type of things. Previously, I was a technical director, a high technical position at TRC Corporation, and I spent 19 years as a senior research engineer at the Army Research and Development Center. So you guys are probably familiar, obviously, with PFAS. The biggest concerns have been from the firefighting applications of these materials, but they're also found in so many others. It's a huge problem. I'm sure almost all of you are going to be running into it if you haven't already, sooner or later. And PFAS contamination is quite widespread. There's over 700 confirmed military sites, but there could be many, many more. And if we start then looking at the civil possibilities, it's estimated over 50,000. They're found in drinking water systems, and also a big impact is in landfills and wastewater treatment plants. So there's a lot of potential places that that we are finding these and are going to continue to find them. I'm going to start with water, and there's a lot of different types of water that may need to be treated. Drinking water usually is good water quality to start with, so that can be kind of straightforward to treat. But obviously, the big issue might be that with drinking water treatment, there's no room for error. We have to get to the MCL and preferably non-detect. Really, people don't really want this in their water at all. And then water remediation, from remediation can vary quite a bit in its quality, so it may need additional treatments. Municipal wastewater, definitely has a lot of, even after treatment, has a lot of stuff in it. So this treatment can be very challenging. So could industrial wastewater, landfill leachate. And then, of course, equipment decontamination usually is pretty concentrated. So there's different types of approaches that can be used for these different kinds of water sources. And by the way, please um, um, don't hesitate to answer questions while I'm doing the presentation. We don't have to wait till the end. Um, I may not be able to see if you're raising your hand, so it might be easier just to to ask your question with your microphone. Now, so PFAS now has drinking water standards. They were set in April 2024. They're quite low for 4 nanograms per liter for PFOA and PFAS, PFNA, PFHS, HXS, and Gen X also are at 10. And then for the first time, there's this hazardous index that's used that is based off of several of these species, PFNA, PFHXS, and Gen X, but also includes PFBS as well. And it has a calculation that also must be passed to meet the drinking water standard. That's the first time it's ever been done for drinking water standard. So these are official drinking water standards, but there's a timeline for water treatment, public water treatment facilities, and from what I understand, that's any water facility that has 60 or more connections. They need to by 2027 complete monitoring for PFAS and release those results to their customers. Now, they don't say the month. The EPA is kind of like that sometimes. They say they're going to do it, and then it may end up being the due date may be December 2027, or it could even run into 2028. But this is currently what any public water supply needs to be planning to do this monitoring. And generally, we're probably looking at a year's worth of monitoring because water quality can change depending on over time. Like, for example, landfills can move up and down over the year. And maybe as it goes up in water level, it could start reaching a PFAS contaminated zone. And of course, the plan would probably have to be cleared by either the state or EPA. So it'd be very important to make sure that that's done ahead of time. By 2029, the public facilities will have to have a plan, an action to meet the MCLs. And then by 2029, and once again, there's no actual month or whatever, they will have to continue to do monitoring, and if they exceed the MCLs, take some sort of action. And so in terms of this is just another graph showing some of the similar things, but it also shows that the EPA has come up with drinking water health advisories for PFOA and PFAS, and they're far lower than the MCLs. So normally the EPA has relied on risk assessment data to set their MCLs, but in this case, these numbers were so low that they actually did a higher number based on the ability to analyze the compounds, which kind of opens with the question, if the analytical processes improve, would the EPA consider going lower? And I think nobody really knows the answer. And in addition, there's also these regional screening levels for PFAS and other compounds, PFOA, for PFAS compounds. They could be maybe used as a starting point for remediation type projects. Most DoD projects that have focused on water have used 70 nanograms per liter as the remediation goal and continue to do so for now. So some of the technologies include granular media separation, very simple, just put something in to absorb the compound. It's very established for PFAS removal, can meet low levels pretty fast, and it's very effective for PFOA and PFAS. It starts losing some of its effectiveness for some of the shorter chain PFAS, which are currently not being regulated, but still could be a goal for a project. Um, doesn't require a concentrate, and maybe for a larger system, regeneration could make sense. It doesn't destroy the compound, it just concentrates it. The media will have to be replaced continuously over time, and the process has to be monitored because as it gets filled, you could have some breakthrough. Um, This is a picture of a system at Orange County Sanitation District using ion exchange resin. And some of the materials, the two most popular are activated carbon, um, very strong absorptive material used many, for many years for a lot of different applications, and specialty ion exchange resins, which are designed to actually work both a combination of ion exchange and adsorption. So they kind of work similarly in some ways to activated carbon in that they absorb PFAS, but they also have that exchange component, which tends to actually help them do a little bit better with the shorter chain compounds. And they tend to have a little bit higher, maybe not even a little bit, actually significantly higher um, capacity than granular activated carbon. So they're sort of a balance. Activated carbon is cheaper than ion exchange resin, but ion exchange resin can have a higher capacity and maybe remove shorter chain compounds. So it just really depends on the goals of the project. In the short term, ion exchange might use a smaller system and be cheaper to build. But then as you kind of start factoring in the change outs, you may find that the GAC is better. And when I was at the Corps, we did some testing of different resins different carbons that were used by the Corps or wanted to use. And we found that the Calgon carbon F400 had a significantly higher absorption capacity than the other ones that we tested, like TIG and I think Avaqua. But once again, it comes down to cost too, because maybe some of them could be cheaper still and still turn out to be a bargain anyways. Some new stuff to look at are clay materials, zeolites, biochar, graphene. Graphene actually has a very high sorptive capacity for stuff. And so we may end up seeing some interesting graphene products in the future. MOFs, metal organic frameworks, and hydrogels. And I'm very interested in biochar for treatment because it's cheaper, and kind of did my own kind of calculation on comparing biochar to GAC. And even though you'd have to use more biochar, there is a potential for reducing the costs for biochar. So I think biochar could be useful maybe for remediation or maybe for water treatment in conjunction with maybe ion exchange or GAC as a material there. So we'll keep an eye on this material and see how it does. Membranes work, obviously. They're very effective for treatment. The technically nanofiltration should be good enough, and reverse osmosis even better. But the big challenge with membrane technologies is the generation of the concentrate, because even a small amount of even if you're saying, okay, we're getting 90% treatment of the water is being treated, 10% can still be a huge amount of water. So that's really been the resistance to membrane treatment for PFAS. There are some places that use it, but usually they're kind of more wealthier, I guess, water treatment districts or communities. Most of the time, the focus has been um, on the granular media treatment. But some possibilities could be like closed circuit reverse osmosis, which generate very, very little waste. But they do have the disadvantage of being extraordinarily expensive. And another technology that really has come a long way is the surface active foam fractionation. Basically taking advantage of the fact that the PFAS is a surfactant, it bubbles, and you can then collect the foam. And if you just do it one time, you can get rid of a good chunk of the PFAS, but it's not really, but the concentrations are still kind of high. But if you kind of do it sequentially and continue to apply it and possibly use additives as well, they can actually reach pretty low nanogram per liter levels. And some studies I've seen have actually met the drinking water standard. So it could be a very nice technology. And one nice thing about it is that it's less prone to competition from other types of materials because like when you're doing sorption or granular media, you're taking out other stuff too, and that's part of your system. But when you're doing SAF, you're really focused on whatever can foam. So that's mostly the PFAS. There could be some other constituents, but that's the advantage of the SAF system.
So
And
Victor,
then
we have a
oh yeah,
question in the chat.
yay. Okay.
So the question is, how do PFAS or PFOS affect the longevity of membranes? How often do they demand changing the membranes in contrast to highly offered efficiency?
Um, so um I my limited experience, and I have done some experiments. This one down here is an experiment I did here with PFAS removal with membranes, but that they the compounds don't seem to appear to have any issues with degrading the membrane or anything of that nature. But they are fairly, they are kind of long chain polymeric type compounds. And so there would be a need that they could be uh, a, their fouling could be an issue. But using, appropriate backwash um, um, plans should be sufficient uh, to extend the life of the membranes and then and be an effective treatment technology over time. That's my that does that answer the question?
I believe so.
Yay!
Yes,
Okay,
you.
thank you. Okay, so residuals, there's all kinds of stuff that's generated a lot of these things I just talked about, none of them destroy the compound. It's just left there. So even if we do a regeneration, that does reduce the volume, but the regenerant is full of PFAS, so we need ways to get rid of it. Incineration is one. However, the DoD has suspended incineration for DoD sites. Now, it doesn't apply to other sites, so non-DoD sites could still use incineration, and I expect that eventually it'll come back to being used because there's just so many. It's they just need something that really works. Pyrolysis seems to have some potential for destroying PFAS. Landfills, like the U.S. Ecology Nevada Waste Landfill is touted as a suitable landfill for PFAS and accepts PFAS contaminated materials. Um, there is always the risk with landfills that they may not, that they may not work, and then you can be on the hook. The customer can then be on the hook for the long-term liability. Cement kilns, I mean, it seems like these can be very effective. It's perhaps a future development, but on the other hand, maybe the cement kiln people might not want to be fooling around with PFAS. And then deep well injection is really kind of taking up a lot of the slack as hazardous waste incinerators have had to be, offline for DoD operations. So they they are, the idea is to inject them so deep that they are below any kind of drinking water wells, but there is now concern that some of these deep well injection sites are getting overpressurized and could actually provide some contamination migration. There are some destructive technologies. Several were tested when I first got involved in PFAS, like around 2012, and we tried to use like all of these we tried to use activated persulfate and Fenton's chemistry to destroy PFAS, and it works. I mean, if you had a site that only had like PFOA, these could actually work, but they don't degrade PFAS. And of course, most sites have PFAS. So that's why they've kind of just dropped off by the wayside. There are some new reactions in DMSO that were published, but they really haven't gone anywhere in terms of having a successful upscaling. Probably the most uh, well studied and maybe most attention is supercritical water oxidation, getting the water to the supercritical point, high pressure and temperature. The water behaves as a fluid. These systems can degrade PFAS. And some of the studies have shown really good degradation. And there are commercial systems that are available, but probably for me, the biggest issue is that these rates for the systems, even the bigger ones, are pretty slow. They don't really, they're usually on the order of maybe a fraction of a gallon per minute. I think there's one General Atomics that's like 3 gallons per minute. And then their value in terms of treating something that's concentrated is kind of not so good either, because often some of the like if you wanted to treat the AFFF material or maybe the fractionated foam, you have to dilute them. They don't work with they damage the equipment if you try to use them in a concentrated form. So then that adds to it, and because of that, the costs for the systems, like if to do a treatment, is quite expensive. So I think it's something to keep an eye on. Maybe if there's a place where you really have like a small amount that you could destroy, it could really work. But I think overall I think there's a lot of limitations at this moment. And the same is true with some of these other technologies, cold plasma analysis, degradation, and some new biodegradation. They they have some successful studies, but upscaling them is difficult. Getting them to meet the actual treatment goal is sometimes very difficult. So I would say these are things that must be proceeded with tremendous care, and because otherwise you could invest a lot into them and not really get what you need. Another idea would be combining treatments like reverse osmosis or a membrane process, and then combining it with like a destructive technology. So that could be something that might be developed very soon, I'm thinking, but in the future. I haven't really seen a successful unit yet. And that was actually one of my goals when I was at the Corps, but now I'm kind of focusing on that is something I'd like to try to put together for a proposal. There are some other ideas, plant uptake, phytoremediation, like uptaking the contaminants in the plants and then incinerating the plants, for example. Partitioning solutions, can you apply like light oils or solvents and then extract those? Or metal adsorption, like zero valent iron, sort of like the old zero valent iron reactive barrier, except in this case, you're just using it to absorb the PFAS. It's not really degrading it. Now I'm going to discuss a little bit about remediation. So groundwater treatment, I mean, right now there's a lot of pump and treat going on. It's not really a treatment, it's more of a containment process. Physical containment processes could be also used as well to keep the PFAS from migrating into the wrong places. Though that's a viable strategy. In terms of treatment, there's not a lot, but here's a few things that have come up. There's one of them is this plume stop material, which is a powdered activated carbon material, liquefied powdered activated carbon that is being injected into aquifers and appears to work pretty good. It definitely seems like it reduces the PFAS migration and seems to have potential for longer life. There's some new products that are similar, made out of clay materials. In situ senolysis is something that is being studied, I think, up in Clarkson University. And I think they've had some success and some other challenges. But senolysis is a use of sound waves to create microbubbles, cavitation that create reactive oxygen species, chemical treatments. And as I mentioned, the big problem was on those was the inability to degrade the PFAS compound. For surface water, containment could be very important. The use of runoff ponds or storm control systems could be valuable for soils that are that contain PFAS. And for this small accumulations, when I was at the ERDC, we developed the PET system to treat them using ion exchange resin, a reactor system to treat runoff collection ponds through in Florida, Japan, and Tennessee. So that's something to consider if you have a small accumulations of PFAS. And then sediments, if we talk about that, the key to that, to dealing with sediments or soils for that matter, is size separation. You want to separate out the sizes. Usually the more larger materials, they may not need treatment, or you could get by with like a rinsing treatment. But then as you get smaller, you may need like something like sediment washing or thermal desorption, which is getting more popular. Also, often for sediments, what they do is they mix in activated carbon into the sediment, and they actually apply that with the idea that the carbon can capture the contaminant and keep it in place. One of the more interesting developments in sediment is the smoldering combustion for soils and sediments. It's they describe it as like making the soil into like a briquette. They typically mix in something like activated carbon into the soil, and then they like kind of heat it with low oxygen, so it kind of burns all the way up, and it's actually pretty effective. It's something to definitely consider. And low temperature thermal desorption also has had some really good successes for removing PFAS. And then you'll need to capture it. It doesn't just, so the smoldering combustion destroys the PFAS. The low temperature thermal desorption desorbs it from the soil, but then you have to capture the PFAS and dispose of it after that. Another material kind of similar to those is a fluorosorb, which seems to also have some very interesting results in terms of being a good material to stabilize PFAS in soils or other materials like that. And decontamination of firefighting equipment. This is a process flow diagram I designed to do that. Basically, you usually use multiple flusses to remove the PFAS and then collect the water, and you can actually treat it and reuse the water if you want to. So you can do the treatment. There are people who have kind of discussed the use of additives. Um, they are expensive, and it's not really clear how well they work. But on the other hand, maybe it's better to use them if your customer can afford them than not. And then these are the methods to see if the treatment is working. 537.1 is the one commonly used for drinking water. There is another one, 533. 537.1M is kind of phasing out because it was really designed to fill a gap until EPA 1633 was developed, and now 1633 is developed and is commercially available. So that would probably be the one to use at this point. So drinking water, 537.1. Everything else, including wastewater, soils, animal tissue, 1633. That's one of the challenges with PFAS is that there's no online or quick way to get it analyzed. It's all done by this LCMSMS. And I mean, if you're lucky, you can get a 2-week turnaround time. Although some labs are improving, but usually you're looking at a month or more. And then the total oxidizable precursors give an idea of materials that can combine and form PFAS. So this is also sometimes commonly used in studies for spills and such like that. And then another concept is using point of use or point of entry treatment for communities that may not be in a position to upgrade their water treatment systems. So this could actually be an important tool as a means of dealing with PFAS. Obviously, another way to deal with it is just to provide everybody with an alternative drinking water source. But these systems can be very valuable. I've seen some programs like in New York City, not New York City, New York State and New Jersey, where the state is helping people install these kinds of systems. And some university research to watch out for: plasma destruction, sonolysis, metallic reactions, and photochemical reactions. All seem to have some promise. So we'll just keep an eye on them, but they also, are still in the experimental stage as well. So I'm summarizing. There are some effective ways to treat PFAS. Most of them involve just removing the PFAS and concentrating it. The destructive technologies, I think, still need some work, particularly getting them to work at a higher rate. But as time goes on, hopefully those will catch up, and there will be some destructive techniques available that are cost effective. So I wanted to move on now to me, my company, Medina Doyle Technologies, LLC. We build water treatment systems, and our beachhead market are these small systems, the PETs and DETs, and the pewter. And we just call them all now PETs, just to kind of keep it simple. But the PETs treats PFAS. It's a mobile water treatment system. It can run for anywhere from 2 to 20 gallons per minute. The DETS, the pewter, which is like the PETs, except it's built in a shipping box, and so it's designed to more stay at one site and treat water, whereas the PETs is designed to move around. So it can be very helpful if you have multiple sites that need treatment. You can go ahead and split the costs, I guess you might say, of the treatment with a single system, and result in some significant cost savings. And then the DETS is similar to these, except it's actually got more, it has a reverse osmosis treatment system on it. So it can treat anything, really. That's what it was designed for, actually. It was designed to treat anything in the water from chemical and radiological weapon decontamination. So it's designed so that no matter what's in there, it'll get it out. So the DETS itself probably is more of a platform that we can use to adapt for other things, like adapting for emergency response type things, desalination, small scale desalination, that kind of applications. And we have all of these have technical reports and data to show their effectiveness. And these were some of the organizations that funded our work. And these are some of the demonstrations that were conducted on these units to show their effectiveness. And this is results from one of our most recent tests in 2023, treatment of a runoff collection pond from a firefighting training area at Tyndall Air Base. So this was a firefighting training area, and it had a system that would return the water to a pond. The pond would had an evaporation system which would further concentrate the water. So this would be a water that you would never use for drinking water. But we had a pre-treatment system, like to remove like petroleum, metals and such like that, and it worked quite well. We were able to meet all the MCLs for that, but it didn't really remove the PFAS very much. This kind of shows that what we got into our pre-treatment system was pretty much what came into our PET system in terms of PFAS. But once the PETs was applied, it worked quite well. And in fact, it met all of the MCLs for the PFAS species that we looked at. So this tells us that we can meet the MCL. It's not impossible, probably kind of expensive, but it definitely certainly can be done. Some other things is when we used our systems in Japan, we were excited to go to Japan, but we couldn't because it was a COVID epidemic. So we used video tools, and we were able to train the base personnel to collect to operate the system and use it. So the systems are easy to use. They're not that, and they can be shipped by sea and air. And we've driven them over 1,000 miles. We've operated them for 24 hours. 24 hours operation, and they have met the EPA MCLs. We have a technology transfer agreement for these, for the PET systems from the Air Force Civil Engineering Center. So we had to meet specific criteria from them to obtain the agreement, like treating below 70 nanograms per liter, being able to be towed by a 1-ton truck, that type of stuff. So we've already done that. So that should help lubricate the process of adapting them. The projects have been funded by the DoD, so we have data. So it's not like, I mean, it's not saying that a pilot project wouldn't be a bad idea, but it may not necessarily be necessary. And that we've done customer discovery with through ICOR and through conferences, and have gotten positive feedback, and that these processes are scalable. So even though our systems are kind of small, our plan is to build any size system actually that we can provide and treat different types of applications. Also, I want to point out that the system is adaptable. Some of the things we're looking at is maybe making it smaller for mobile water for military operations, or using our systems, maybe changing out the media for disaster response, which or desalination, like particularly in Louisiana, where they're having a lot of problems with seawater encroachment into their aquifers, fracking water, or valuable mineral recovery. The same types of processes that we use in our system can be used to treat other kinds of contaminants and other types of uses. And we also are developing a business for a point of entry system. We call it the Magnolia Poet, which could be used to treat contaminated water in coming into homes or into a number of homes. I think this could be very helpful for like military housing applications, for example, as well as communities throughout the United States. I think that's all I had today. Thank you. We have some time for questions. I would love to hear any questions or thoughts. Thank you very much.
On the those mobile treatment trailers you have, what kind of flow rates can they handle?
Yeah, they run right now. Those systems I showed run between 2 to 20 gallons per minute. And a lot of it just depends on, like, if it's a fairly clean water source, we can go like to 20 pretty easily. But like the source at Tyndall, we had to run closer to 2 gallons per minute because it had so much stuff in it. It could overwhelm the system. So, but those can run between those levels. Um, and we did projects where we treated. I mean, we are a research organization, but we literally pumped out the entire contents of the Hurlburt Field water collection pond. So, I mean, it's basically like a remediation for that pond. So we certainly, even though the rates aren't exactly the fastest, they're fast enough for those types of applications. Mhm.
How are you advising the local water suppliers on what costs they should expect if they have to implement this on a larger scale?
No, that's a good question. I think I think a lot of them are going to be pretty bummed out. Because here's the thing, the actual treatment systems, there's not a lot to them. Um, so the initial capital costs probably aren't too bad. They'd probably be, something that they would, might be okay with. But the continued costs of operating the systems and replacing the media is going to be a real challenge over time. So I think
Victor, are you saying for the large scale water systems to go with the GAC and then wait till the on-site destructive processes are worked up and deemed efficient?
Probably, I would say probably consider, well, I would say either GAC or ion exchange. It would probably come down to um, uh, uh, life uh,
Life cycle cost.
uh, yeah, analysis, LCA. You would do that. And also a lot of it might be like, well, what are you thinking of the future? There is some thoughts that as time goes on, the EPA might try to um, change some of the requirements. I don't think they will, frankly, but there is some concern about that. Or states might have more stringent levels themselves. So,
I don't know how you can get more stringent than 4.
well, you can't right now because you can't analyze it. But yeah, I agree with you on that. Um, so, Chris, yeah, I think it just really I think you should consider all the options, but I'm probably with you. In most cases, it's probably going to be GAC if you're really looking at the long-term operation of it.
I agree. And then keep our eye on the destructive methods and see if there's a practical solution. Because the GAC doesn't solve the problem. You still have the contaminant and you're going to have to follow that and get it destroyed at the end of the day.
That's right. Yeah. You're right,
And
Chris.
and
So,
and I think we're starting with water, but it's quickly going to go to the sewer plants, and you're going to have to get it. I'm just amazed we're going back to incineration of solids. I feel like the 1950s are coming back to us. I mean, it's a little crazy.
there is a lot of concern about the incineration process, no question about it. Maybe there'll be some new developments in that area. I do think that the combustion technology is very interesting and could be maybe useful in that area. And maybe cement kiln reactions could be useful. But there's a lot of challenges like, well, do you really want to have contaminated water brought to your cement kiln? So, but yes. Um, any next question, please?
I think you answered all the questions already, Victor. Was that good of a presentation?
So a couple of things I just also wanted to point out that I hadn't had a chance to really include on this. There's another technology. There are some new photocatalytic technologies that are being proposed. One of them is the PFAS and they have claimed some really good results. I'm not really, but I haven't really seen anything more from the like on the area of being a um, like a paper or a scientific document that to confirm that it's very as effective, and also like most of the destructive technologies, I tend to be a little bit leery of their rates and wondering if their rates are sufficient. Um,
So from just to summarize what I'm hearing, Victor, like I'm by no means an expert in water treatment, but it sounds like 3 years or 3 to 4 years, they need to be able to treat pretty much all the water in the United States for drinking consumption. And there's no
the
technology that's
estimate is that
gained.
it's going to be about 40% of public drinking water um, uh, systems will 45%, I believe, actually, is the estimate that 45% of American public drinking water systems will need um, treatment. So now we'll see. I mean, it very well could be more, So yeah.
And
I
there's
think the
no
most difficult part of this is the detection of the PFAS. I don't know how many labs are certified by EPA to do the detection or analyze this PFAS level. I mean, it's parts per trillion. Last time I went
That's
to a
right. Yeah.
seminar, they said finding the PFAS is like finding a few cowboy hats in the size of Texas.
Yes,
So,
so yes, Mr. Chen, Dr. Chen, it is a challenge. There are companies. So right now, there is actually a certification process that is used to determine if the labs can do it. And probably the most common one is called the DoD ELAP program. So labs that are certified by that program usually can reliably, at least, they have a certification that says they're getting the right numbers. Some of the labs I've used in the past, I tend to use Eurofins. I tend to use them a lot. But PACE is another one. Shoot, there's a couple of others as well. But that is a problem. Do we have the capacity to analyze more samples? Because there have been times when we've had to wait like 6 weeks or 8 weeks, to get results. It can be a while.
Are those labs certified by EPA?
Yes, they are, and DOD.
Okay.
So yeah, so the one I tend to use the most is Eurofins. There's a couple of others. Well, there's probably several, many others. It is a business that people are getting into and developing capabilities, and there is a process to become certified. So you have to pass it, but the problem is that some of these labs, their capacity's improved a lot, um, but with the new needs for sampling, because not only now has the EPA regulated PFAS as an MCL for drinking water, but they also have now listed both PFOA and PFAS as CERCLA hazardous substances. So that could also generate a lot of additional needs for studies, like um, remedial investigation studies and stuff like that. So the capacity is a problem. The capacity from labs, and also the capacity for treatment, because as I told you in the beginning, I worked for a while, about 2 years, as a technical director for PRC. It was if we had projects where we wanted to get estimates for PFAS control equipment, and it would take either no response or like weeks of response times from very well established companies. So that's another real challenge, is the capacity for um, all phases of the work. And then in addition to that, there was at one time, and it may still be a problem, a shortage of granular activated carbon. So, um, and that's kind of the driving things, like, well, let's see if biochar can work, or, other materials. Those are kind of, I think there's going to be a place for those, because and part of it is going to be that the granular activated carbon and the ion exchange companies might not be able to keep up, and there'll be a need for something different.
I have another interesting question. Has EPA detected PFAS in the air?
Oh yeah, well, I don't. I mean, it is in the air. Yes, it can be vaporized. Um, I don't know if it's just like in the air we're breathing right now, like, as opposed to water. But certainly that's a concern with incineration, is that not all the PFAS is getting destroyed and is being released into the air. That is a concern for worker health safety. Is that there could be PFAS vaporized. And then clearly PFAS is getting into our hydraulic cycle, which includes the clouds, because they're finding PFAS in both Antarctica and the Arctic. And that's the source, is that it's getting into um, clouds and such, and then eventually precipitating or being deposited in those areas. So the whole world, unfortunately, is contaminated with PFAS in some form or another. I mean, when I say contaminated, I don't necessarily mean that it's above the EPA levels, but there is some. I just saw somebody today on LinkedIn who posted that she did her own blood test for PFAS, and she says she doesn't use nonstick cookware or whatever. And I mean, she had small amounts, but definitely measurable amounts of PFAS in her blood. Any other questions?
All right. Well, thank you, Victor. That was a great discussion and great presentation. We appreciate it.
If you have any others, don't hesitate to contact me. I gave Coraggio my presentation, and I asked him if he feel free to share it. It has my contact information on it. And I'd be glad to talk to you anytime. Thank you.
All righty. Thank you, sir.
All
Thanks
right.
a lot for joining us, everybody.
Thank you.
Thank you, everybody.
Thank you.
Thanks for organizing it, Coraggio.
Thanks. Take care.